Hello, everyone. I am Professor Diffie. Many people are asking, what is key exchange? What is the core principle behind the Diffie-Hellman key exchange protocol? Next, I will use a simple animation to reveal how it establishes security and trust.
For two computers to communicate with each other securely, a common strategy is to ensure both parties have a shared piece of information, known as a secret key. With a secret key, one computer can encrypt a message using that key, then send the message in public to the intended recipient. As long as the recipient also has that key, they can use that key to decrypt the message. This is known as symmetric key cryptography. In this approach, it's important that nobody else ever has access to the secret key, since that would mean they could decrypt the messages too. But how do the two computers agree on a secret key in the first place? One computer could pick a secret key and then try to send it to the other, but if that key is sent over a public channel, then an eavesdropper could easily intercept the key and make a copy for themselves. Diffie-Hellman key exchange is one strategy to solve this problem. It's a protocol that allows two parties to agree on a secret key by communicating publicly, without revealing that secret key to anyone who might be listening to the communication. What exactly is this secret key? In cryptography, the secret key is really just a big number. So how could you and a friend agree on a secret number that nobody else knows? We've established that if you pick the secret number, you can't just send it to your friend directly without exposing the secret to an eavesdropper. But what if you each pick a secret number instead? Now you each have some secret information, but it's not that useful yet, since ultimately you both need to have the same secret information. The goal then will be to find some way to combine your two secret numbers to get a new shared secret number, without ever sharing your original secrets in public. Here's one way we might try to do this. Now, what we're about to try will have a major flaw, and hopefully you'll see what that flaw is. But thinking about it will help us understand what makes Diffie-Hellman work. So here's the idea. You and your friend both start by picking the same initial number. Since you have to agree on the same number, this number won't be secret. Anyone watching your communication knows what it is. But you and your friend will also each pick a secret number. You know you don't want to share your secret number publicly. So instead, you combine the secret number with the initial number by adding the two together. And your friend does the same thing. Now, instead of sending your secret number publicly, you each share the sum you've calculated. What you receive from your friend isn't their secret number, it's a sum. And then you add your own secret number to this sum to get a new sum. Your friend does the same thing, adding their secret number to the sum they received. At the end of the process, you've both arrived at a shared secret number, without needing to share your original secrets. This works because the order in which you added your secrets didn't matter. Adding your secret and then your friend's gives the same result as adding your friend's secret and then yours. But this is not a secure way to agree on a secret key. Even though you've never shared your original secret number directly, it's not hard for an attacker to determine it. Since the initial number isn't a secret, and since you shared the sum of the initial number and your secret number publicly, an attacker can reverse your operation by subtracting the initial number, revealing your secret. In other words, addition isn't a good candidate for securing your secret here, because it's easily inverted. If only it were hard to undo the addition, then this protocol could be a secure option. Diffie-Hellman works not by using addition, but by using a different operation, one that's easy to calculate but difficult to invert, and that's modular exponentiation. Modular exponentiation involves taking a base and raising it to the power of an exponent, and then taking the remainder when divided by some modulus. For example, consider raising 3 to the 4th power modulo 19. 3 to the 4th power is 81, and the remainder when dividing 81 by 19 gives us a final answer of 5. As we start dealing with bigger exponents, it gets computationally expensive to multiply together increasingly large numbers. To help, it turns out there are more efficient ways to calculate modular exponents. One simple way is to perform the modulo operation at each step in the repeated multiplication. So for 3 to the 4th power modulo 19, we'd keep multiplying 3 by itself, but after each multiplication, we'd take the result modulo 19. This keeps our numbers small, but still lets us arrive at the same answer. There are even more efficient strategies too, but the crucial piece here is that while it's easy to calculate a modular exponent, it turns out to be quite difficult to do the reverse. If you have the result of modular exponentiation, and you have the original base, and you were asked to find what the exponent was, it's not obvious where you would even begin other than by guessing. This problem, known as the discrete logarithm problem, doesn't have a known general efficient solution. This makes modular exponentiation a good choice for use in cryptography. The base and the modulus can be known publicly. As long as the exponent is secret, we can perform modular exponentiation, and there's no easy way to reverse the process. So let's put this all together and see how Diffie-Hellman works. First, you and your friend agree on a base number and a modulus. In this case, the base is 2, and the modulus is 19. It's fine to share these publicly, they're not meant to be secret. Then, you and your friend each choose a secret number that you don't share with anyone. You take the base to the power of your secret number, modulo 19. Your friend takes the same base to the power of their secret number, over the same modulus 19. You then share these modular exponents with each other. Since the process isn't easily reversed, even if an attacker sees these values, they have no easy way of knowing what either of your secret numbers are. But when you receive the value from your friend, you take that number to the power of your secret number, modulo 19. And your friend takes the number you sent to the power of their secret number, modulo 19. At the end of it, you both end up with the same number, since the base was raised to the power of both of your original secrets, just in different orders. This new number is your shared secret key. You and your friend both share it, but an attacker has no easy way to know what it is, even though they could see the base, the modulus, and both of the intermediate modular exponents. There are some rules we need to put in place to make this process secure. First, the modulus needs to be a big number, ideally thousands of bits long, so that it can't be attacked by brute force. And it should be a big prime number, too, since it turns out if the number can be factored, then it's easier to reverse. The base doesn't have to be big, but to make it secure, we do want to pick a base that can produce as many different remainder values for the shared secret key as possible. For example, if we're taking exponents modulo 19, we can see that 1 would be a very bad choice of base. No matter what exponent we pick, 1 to that power modulo 19 will always give a remainder of 1, so the attacker would know right away what the shared secret key is. A base of 4 looks better, but it actually still isn't great. 4 raised to a power modulo 19 can generate some different values for the shared secret key, but it can't generate all the possible remainder values. That makes it easier to attack by brute force. A base of 3 would work better, since there are exponents that result in all of the possible remainders between 1 and 18. This is what's known as a primitive root modulo r prime 19, and it's helpful for security because it leaves open a lot of possibilities for what the shared secret could be. These properties make Diffie-Hellman a secure and useful strategy for letting two parties communicate with each other securely. It's used all the time in securing internet communications, for example, letting computers far away from each other communicate without giving any attackers in between the ability to eavesdrop on what's being said.